Welcome back. Let's resume. In the previous video, we talked about the graphs of sine, cosine, and tangent functions. Here's a review. Here is the graph of sine function going up and down and up and down and up and down, starting from the origin. It's an odd function. Maximum is -1, the minimum is maximum is +1, and the minimum is -1, and the graph bounces back and forth between those two. This is a graph of cosine function going up and down, same way, except that this is an even function, starts at 0, 1, which is maximum, and then start from decreasing. Now here is the graph of the tangent function. In the principal domain, negative pi/2 to positive pi/2, we have this increasing behavior, and at negative pi/2 and positive pi/2, the tangent function is undefined. Therefore, we have vertical asymptotes. As a matter of fact, I said it backward. They have vertical asymptotes. Therefore, the tangent function is undefined. The reason it is really undefined there can be best explained by this, as a matter of fact. Let us draw the graphs of tangent function, sine function, and cosine function together in the same viewing window. And we can make this observation. Tangent of theta is defined by y/x, and let's algebraically manipulate this a little bit. Divide both numerator and denominator by r. Then we have y minus r over x minus r. Because I divided both numerator and denominator by the same number, r, I didn't change anything, so equality still holds. Now let's make this observation. What is y/r? That's sine of theta. And what is x/r? That's cosine of theta. Because of that, tangent is sine over cosine. Therefore, the graph of tangent function is intimately related to those of sine and cosine. The most conspicuous thing about tangent is the vertical asymptote, of course. And that's when the cosine function hits 0, and it is clearly visible here. The denominator is green, and when that hits 0, we have the vertical asymptote. Also, please note that when the blue function, the tangent, hits 0, the numerator, sine function, also hits 0. Clearly visible in this visualization. Okay, sine, cosine, and tangent, we have pretty good review, and let's move on to the other trigonometric functions. Cosecant is one over sine, and why is that? Oops. Cosecant of theta is defined by r over y, isn't it? And that's the same as 1 over y over r, which is 1 over sine of theta. So with really simple algebraic manipulation, we just prove that cosecant is equal to 1 over sine of theta. And oops, what did I just do? And that relationship must be visible in this graph. When the red function, which is sine function, hits 0, we have to have the vertical asymptote because denominator becomes 0 there. And that's clearly the case here. And also, at 1 and -1, the red and blue graphs touch each other because 1 over 1 is 1 and 1 over -1 is -1. And that's when sine and cosine, that's when the sine function is reaching maximum and minimum respectively. And consequently, that's when the cosecant function reaches the local minimum and local maximum respectively. Now here is the relationship between the graph of secant and graph of cosine function. And it follows from the same logic. Secant of theta is r over x by definition, and that is equal to 1 over x over r. Consequently, this is the same as 1 over cosine of theta. Again, by really simple algebraic manipulation, we just prove that secant is 1 over cosine, and that relationship must be visible in this graph. Well, let's check. When the denominator, cosine, hits 0, do we have the vertical asymptote? Yes, we do. Now, finally, let's move on to the cotangent function. Oh, excuse me, I made a typo here. Cotangent is 1 over tangent. Okay, and cotangent of theta is of course defined by x over y. Consequently, this is clearly 1 over y over x, and y over x is tangent. And that must be visible on this graph here. Brown is tangent and blue is cotangent. And when tangent function hits 0, we have vertical asymptote. That's when we have denominator 0 situation. And also, when cotangent hits 0, we have to have vertical asymptote for this brown dotted curve, because again that's reciprocal, so tangent is undefined when cotangent is 0 because denominator becomes 0. Another important relationship for cotangent is the relationship between cotangent with cosine and sine. So cotangent is cosine over sine, and you can easily see it like this. Cotangent is by definition x over y, and divide both numerator and denominator by the same number, r. Consequently, I don't change anything. And x over r, what is it? Is cosine, and y over r is sine. So what did you just do? We proved this one as well. And let's see, do we have that relation? Cosine is green, sine is red, and the denominator is sine function. So denominator hits 0 precisely when we have the vertical asymptotes. Do we see that? Yes, we do. And then the numerator hits 0 precisely when we have 0. Do we have that? Yes, we do. So there goes the graphs of cosecant, secant, and cotangent functions. Okay, we have plenty of time left, so let's talk about some trigonometric identities. We already talked about how we end up with cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent. We already proved those over there. And then we did the same thing for tangent is equal to sine over cosine, tangent is cosine over sine. I have those here, the same thing. Among those, this one is more important than the others, so I made a big box on it. The others are relatively important too, but tangent is equal to sine of cosine is really important. Frequently I call it the formula number 2 because it is arguably the second most important identity. What is the most important? Formula number 1? Well, it's this one. Cosine squared plus sine squared is equal to 1. Why? Well, cosine squared plus sine squared is by definition, well, cosine is x over r, isn't it? So that's equals to x squared over r squared, because x over r total quantity squared is x squared plus r squared. And sine squared, that's y squared over r squared. Y over r total quantity squared. And then if we take the common denominator, we have x squared plus y squared over r squared. Now, what is x squared plus y squared? Please note that everything is coming from a circle of radius r centered at the origin. So x squared plus y squared is equal to r squared. So we have to have r squared over r squared, that's 1. So this was a little bit tougher proof, but still it was one-liner. And this is the formula number 1, by far the most important identity in trigonometry. And another implication here is that sine squared and cosine squared are interchangeable. You can express sine squared and cosine squared kind of like these two. Just a moment. I have to take care of some symbols first. Okay. And because of that, you can rewrite cosine squared of theta as 1 minus sine squared of theta, of course. So if you have cosine squared function, and then if you have to rewrite it, re-express it in terms of sine, you can use this. And vice versa too. Sine squared can be rewritten as 1 minus cosine squared if necessary. So depending upon the circumstance, when we have to express sine instead of in terms of cosine, you'll have to use this. When you have to use when you have to express cosine in terms of sine, you'll have to use that. So that's one of the implications. Cosine squared and sine squared are interchangeable. And also, here's the proof. Here's the second Pythagorean identity. 1 plus tangent squared is equal to secant squared. And this one is a little bit less important compared with the original Pythagorean identity, cosine squared plus sine squared is equal to 1. So I did not box it, but this one is moderately important too. And if you want to prove it, you can prove it like this. By the way, this upside down 3-dot triangle means because of this relation. 1 plus tangent squared can be rewritten as 1 plus y squared over x squared, because y over x is the definition of tangent. And we do the same thing, take the common denominator, basically the same technique as before. And we have x squared plus y squared over x squared. And the numerator, x squared plus y squared, is r squared. X and y, x comma y is coming from that unit circle. So what do we have? R squared over x squared. R over x is secant, so we have secant squared. This is one way to prove it. Another way to prove it is to do this. From the first original Pythagorean identity, cosine squared plus sine squared is equal to 1, divide both of them by cosine squared. And cosine over cosine is just 1, and sine over cosine is tangent, and 1 over cosine is secant, so we end up with the desired identity. You can do something similar to this one. You can prove it either directly using the definition, or you can start from the original Pythagorean identity and divide both of them by sine squared. Either way, we'll have this cotangent and cosecant identity.